Okay, so now at least we have two options in order to perform our inverted indexing on secondary memory, and thus in principle we do not have any issue in terms of the size of the inverted index. I say in principle because clearly if you consider I don't know, as an example, the World Wide Web corpus probably does not fit anyway. So that's why we have to consider other possible options which deals with distributed indexing, namely taking advantage of a number of machines and clusters of machines possible distributed all over the world that allows you to perform a task that otherwise cannot be performed in a single machine, even if you exploit secondary memory. Okay, this is the scenario. Okay. Indeed, I would say the classical example is that if you want to do some kind of web scale indexing, this is not possible in a single machine. Furthermore, another good, so the main observation is that you need the distributed indexing in order to deal with modern big data corpus. Consider that in the forthcoming years is envisioned the booming of the so-called Internet of Things, as an example, in which in principle you have billions of connected devices, each providing data. Or if you consider indexing new media, like, I don't know, audio or video, clearly you have an understanding of the fact that it's not possible to deal with with such huge amount of data on a single machine. Okay, so this is the first reason for distributed indexing. Furthermore, a single machine is prone to fault. It can stop working, or can be slow, or even fail, and thus a distributed solution can help to solve those issues. How can exploit a pool of machines? Okay, the first interesting observation is that despite we think about modern server farms are made of fantastic devices, in many cases those devices are pretty common. I mean, I would say good machines, but not particularly different from the ones we can use. In a single word, most of those data centers use commodity machines. They are distributed clearly all over the world. Just to give you an example, and again, we are talking about 2007, so please imagine what we are talking about today. Google was made of 1 million servers with 3 million processor cores. Now consider that even the most simple machine now is made of maybe 7 cores, at least 5 cores, so completely different. About $250 million per year of expenditure, and it was supposed to be 10% of the computing capacity of the world. Do you know what is another very impressive computation factory in the world? True, no, I mean in terms of applications. About one is web searching, another one? Mining, as an example. Now, blockchain mining is it's an amazing font of computational capabilities. Now, what is interesting is what is written here, okay? Now, if you do not have a fault-tolerant system with 1,000 nodes, and say that each of them has a pretty reasonable uptime. Uptime means that it works 99.9% of the time. So it works almost ever. What is the uptime of the whole system? Again, it is not tolerant to failure. If something fails, the system fails. Okay? Surprising is 63%. Okay? Which is actually, if you consider usual service level agreement, SLA is supposed to be 99 something. Okay? And maybe even more interesting is that if you have a server fail after 3 years, so if a server will stop working for some reason, any reason, after 3 years, if you have 1 million server, what is the interval between machine failure? The answer is less than 2 minutes. Okay? So this makes clear that one of our assumptions was, look, we are using distributed system in order to to make the system more reliable. But according to those numbers, there is something that we have at least to understand. Okay, so the answer is very simple. The answer is that you have a master machine that basically coordinates the indexing service, and this master machine is considered safe, so it's fault tolerant, so it's one of those machines extremely expensive, but that works say 100% of the time. And what it does, it breaks the workload into small chunks of parallel tasks, possibly taking into consideration in the scheduling of those tasks what are the machines that are working, what are the ones that are not, what is the load of the machines. Namely, you have a usual, I would say, a scheduling algorithm that takes into consideration all those parameters in order to select what is the most appropriate machine to deliver a given task. So the machine, the master machine, assign the task to one of the machine of the idle machine into the pool. Okay, but what is interesting here is that we are talking about parallel tasks. And so a very short walk through one of the most interesting techniques that has been pushed by Google for distributed computation. And the name of this technique is Mapreduce. So what is Mapreduce? Mapreduce is basically a framework. Maybe some of you have heard about Hadoop, okay? Which is one of the systems which implements Mapreduce. The idea of Mapreduce is that you have a framework that allows you to write application to deal with big data in the strict sense. Okay? Huge amount of data. Taking advantage of large clusters of machines, providing you computation capability, and guaranteeing some kind of reliability. Okay, this is the idea. You have a framework, and there are libraries, as an example in Java, to implement applications on top of those frameworks. This is usually done in big data. I don't know whether you will do it in your classes or not in the future. It is one of the courses provided by, actually, one of the courses given by Luca. So Luca Becchetti is an expert in Mapreduce. Okay, so as you can expect, we have basically two main functionalities: the map functionalities and the reduce functionality. Okay. The map takes an input, a large collection of documents, and provides in output a stream and the streams should be something that now you already heard this afternoon, of key pairs, key value pairs, okay? Key value. So if you think about what we saw before, clearly this stream is familiar, and thus maybe we can exploit this, okay? Not only, the map function also group those key of functions, the map functions also group those pairs of key values into consistent group through the shuffle function, okay? And then you have the reduce. The reduce takes in input the output of the map function, okay? And the reduce function combines all the value of this of the map function in order to provide an output that can be any mathematical function, okay? And it will output a set of distinct key and their corresponding combined value. Now, it looks a bit abstract. Let's make a very simple example, and then we'll see a picture. Assume that you want to sort cards, okay? So the cards have the 4 seats. I guess it's seats, I'm not sure in English, but I guess it's seats. Okay, so the map function will basically provide an input pairs of key value in which you have seed and the value of the card. So, I don't know, heart, and 1, 2, 3, 4, 5, etc., etc. Okay, this is the map function. It takes in input the cards and provides in output the couples of key value. Okay, now we have 4 seeds in this particular case. So I will give to each of the 4 guys here in the first row 1 of the seeds. So everybody will receive the seeds. And then if we want to count the number of cards of a given seeds, the reduce function will simply count those numbers. If we want to count the number of, I don't know, kings of a given of the seeds, I will have a reduce function that will count the kings and stuff like that. Okay, that's basically the idea. So I think this is a very nice picture. Unfortunately, I don't think you see very well the colors. But assuming that you have in input streams of data with different colors. So the map function will simply take this input and will map into 3 distinct queue, each for each color in input. And those distinct queue, by the shuffle function, are provided to the reducer that will simply count the accumulated value for each of the queue. Okay, so map, each value is a color in this example, a queue for each color. The queue for each color from the different mappers are provided by the shuffle function in input to the reduce that simply counts or aggregate those values. Let's see another example. So this is pretty close to what we are actually interested in doing. So we have an input, these deer, beer, river, car, river, and so on and so forth. In the first phase, we split. This is the corpus, right? So we split the corpus. Every mapper will take its input chunk and will basically make a couple in which it will simply say every time it will see a given word. So it will see deer 1, it will see beer 1, it will see river 1. Notice that here we are not counting. We are simply, so the couple counting is a matter of the reduced function. We already see, I see one car. I see another one car. Why? Because we have two of those cars. I saw one river. I saw one deer. I saw one car. I saw one beer in my chunk. Okay, this is the map function. Key value. Okay. Now we have a shuffling in which basically we have a node that is in charge of dealing with beer, and a node which is in charge of dealing with car. Each node is in charge of dealing with one or more values. Okay. Now the reduce simply count, so it sum up all the key observed during the map. And so we have 2 beer, 3 car, 2 deer, and 2 rivers. That's it. Okay? And finally, I will sum up in order to get the final result. Okay. Why is this very convenient?
It allows for parallel computation.
Those are nodes that can be whatever, and each node can do a very simple single function. It can be a mapper, it can be a shuffler, it can be a reducer, or even more than one function, depending on the capabilities. But this can be in Italy, this can be, I don't know, in US, this can be in India, this can be in China. Okay. Providing that you can handle a proper transforming of your problem into the Mapreduce paradigm, you have parallel and distributed computation for free. Does this make sense for everybody? And so you can clearly take advantage of all the resources we discussed before. And this is actually what Google does for indexing the corpus. Okay? So basically, going back to our original goal, we have parallel tasks. Let's have a look to what are the parallel tasks in this particular case. So basically, we have 2 types of machines, the parsers and the inverters. Okay? So those tasks are delivered to parsers and the inverters. What they do is they break the input of document into splits. Okay? The splits are the blocks we saw before, and are actually what we saw here. Okay? The input to our nodes. Okay? Good. And each splits indeed is a subset of documents. So again, here we have the whole corpus. We split it in a subset of documents. Okay? Good. Now the master, don't forget that here the assumption is that we are using commodity machines that are prone to fault. So we have only one single machine, the master, that is fault tolerant. And the master is the ones that simply assign a split, namely a block of documents, to an idle parser document, according to some scheduling policies. What does the parser? It reads the document and emits term.id pairs. Term.id are exactly key value. Okay? Does it make sense to everybody? We saw key value as a general term for the mapping function. In this particular case, the parser does exactly a key value mapping that is made of term.id. Okay? Now, parser write pairs into J-term partition. J-term partition, what are? Are the shuffle we saw before. Are grouping of the key value pairs, namely of the term.id, in which basically you have j, according to the term, j terms grouped together. So as an example, from A to F, in case you have j equal to 3, from G to P, from Q to Z, and so on and so forth. Okay? So, splits, okay, parser, J grouping, and finally reducing. Okay, the inverter that actually does the reducing functionality in this case produce the posting for a given term partition, okay, for a given one of the J terms we saw before, as in this example, the ones from AF. And finally, sorts and writes the posting list. So this is the final architecture. Here we have the corpus. The corpus is split in a number of splits, according similar to the blocks we saw before. The parser, which is the map function, from those documents provides an input doc term pair. The doc term as assigned, term doc are assigned to a given shuffler, which is in this particular case the segmentation, the J segmentation we saw before. This is provided finally an input to the inverter that does the final job. Okay? The real novelty here is that all those nodes can be everywhere. And thus we fully take advantage of the availability of a cluster of machine distributed in a global scale. Questions? Is everything clear? Sure? Good. Okay. Okay, this is one example, but actually it's not, to me at least, particularly illuminating. It's simply an instance of what we saw before. Now, this index construction should be now clear that is an instance of the Mapreduce framework. Mapreduce is a very conceptually simple, and actually the case we are considering is among the most simple implementation of the most simple problems taking advantage of Mapreduce. Much more complex problems requires more effort in terms of understanding how to effectively exploit the Mapreduce framework. Anyway, what is interesting is that you do not have to write the code specifically for the distributed part, okay? Providing that you can map your problem into the Mapreduce framework, you do not have to write something specific for the distributed part. In the Google pipeline, actually there are a number of phases, and each of those phases is implemented with the Mapreduce framework. Indexing is one of those phases. Other possible phases are the transform temp partition into the document partition index, and there are many other phases that are implemented by Mapreduce, taking advantage of the huge computational capabilities provided by the Google infrastructure. Okay, good. Okay, so we started with our framework in which everything was on a single machine. we discuss, and in RAM, we discussed that, okay, very good, but it doesn't work because it's impossible that modern corpus will fit into the RAM. So we discussed how to bring the indexing algorithm in the secondary memory. Then we said, fantastic, but actually even if we can handle this computation into the secondary memory, most likely the corpus, modern corpus, such as the web, does not fit even in the secondary memory of a single machine. So we consider distributed indexing. So let's move in a distributed architecture, and we saw the paradigm Mapreduce, which is pretty convenient in order to build the index. But up to now, the assumption is that the index is pretty static. It's not evolving over time, while it's reasonable to assume that the indexing will evolve over time. So we have a dynamic indexing, and this is actually the goal of this last part of the class. Okay? So we remove the assumption that indexes are static. We consider that documents can be clearly inserted, deleted, or modified, and this brings to the need of both a posting list and a dictionary that dynamically evolve over time. Okay? So the first idea we can explore is very simple. We keep a very big index into the disk. We maintain a small what is called auxiliary index in memory. What is this auxiliary index? Is the index taking care of documents that have changed dynamically in the last period. Okay, that's the idea. And then you treat both those indexes the same way, and so you search, you perform the query on both the indexes, namely the relatively static one on the disk and the relatively dynamic one on the main memory, and then you merge the results. Clearly, after a while, what you have to do is you have to merge both the auxiliary and the big index into one single index and start from scratch. Okay. If you have deletion, namely some documents are removed, you can basically filter the returned docs from a query, removing all the documents that provides us output that are not documents that have been deleted. Okay, you can do post-processing on the query. Okay, the main problem is that clearly you might have very frequent merges of the two indexes, and while you have this merging, which is not actually it's frequent, you might experience poor performances in the query. So anyway, you can think about again, you can deal with those two indexes, but we have an assumption in the rest of the lecture that the index is one big file. Okay? In reality, you might have a number of files that can be processed in order to get the results and that you have to merge together. Now, in order to explore one possible advanced index scheme, we will consider the logarithmic merge. Okay. The idea is that through logarithmic merge, you amortize the cost of merging indexes over time. And since during the merging we saw that the performance of the query system degrades, what we can do is we can amortize those costs in order to provide to the end user better performances. Now, in this case, instead of a single big index as we saw before, we have a number of indexes. Okay? So we maintain actually a series of indexes. And the first observation is that each of those indexes is twice as large as the previous one. Okay, you have a main index in the memory. As soon as you fill up this index in the main memory, you write it into the disk. Okay? This is again empty. You fill up the index in the main memory. As soon as you have fill up again, so you have not any more space, you'll bring it into the disk. But since now this index is already present, what you do is you merge those two indexes, you double the space, and you move on. Okay? And then you start again. Small memory index, once it's completed, now you can write it, because now this is free. Again, it's already taken, so you merge it. This is already taken. You merge it, and you go back. You go forward. Every time, you double the size of the index. Okay, so let's see why is it logarithmic. So assuming that the size of the smallest index is A, so you first use all this A, okay? Once this index is full, you write it into the disk, A. This is again empty now. You fill up it. Once is again, this is at time 0. When at time 1, this is full. You try to write it here, but it's already occupied, and thus you write it in the next position, where is 2A. And this is now empty. Okay. T2. You remove from here and you write here. Okay? T3. Now this is already occupied. This is also already occupied. And thus, you have to write here is, and so on and so forth. Every time you double the space. That's the only trick. And you write down your index wherever you have space. Does it make sense? It's the procedure. So basically what you have here, here you have a binary number in which when you have a 1, when you have a 1, it means that that index is occupied. When you have 0, it's free. In the worst case, you have all 1. Okay? So in the worst case, in order to answer to a given query, you have to see all the indexes. But now, since this can be imagined as a binary tree, okay, this is usually log 2 of t, where t are the tokens, right? Because in the worst case, I have to use all my indexes. Okay? So, let's see. The number of indexes is log t. We saw it. It's like a binary tree. Okay? Do you all agree? Good. Now, so the query processing, in the worst case, you have to see the results, you have to perform the query on all those indexes, and then merge. So in the worst case, again, you have d log t, because you have to see in all the indexes and then merge this stuff. Okay. Why this is interesting? Because the complexity to construct the index is t log t. Why? Each posting is merged in the worst case log t times, right? So for each posting, and we have t posting, is t log t, the worst case analysis. Why? Because you have to merge, if the index, if that term is since the beginning there, you have to merge with all the others. So it's t log t. In the worst case, it's t log t. What was the auxiliary index before? Every time that I fill up the index, which is the same, clearly we are comparing apple with apple, not apple with other things. So the size is bounded by A, which is the size of the main memory that will give to the index in both cases, both with the auxiliary index and with the logarithmic one. In that case, every time you double, and the complexity is square. Okay? Because once it's completed, I'll place it, and so on and so forth. And in the worst case, it reached this place, and so is a multiplied by n squared. So we are now comparing big O of t squared against big O of t log t. And so we have a significant improvement in terms of performance. Of performance of what? Of the logarithmic merging, which is an order of magnitude more effective. Is this clear? So again, every time I fill up, the available memory, I'll move it, and I double the space. Okay? Good. At the end, I have a logarithmic number with respect to the terms. For each term, in the worst case, is t log t, because it's that term logarithmic of t. For each term, in the worst case, is t squared. Why? Because every time I have, initially the size of the index is A. When I completed, I fill it up, the number of the index is 2A, and so on and so forth. So the bound now is square. Okay? Good. Clearly, in general, building indexes is a combination of a number of tools. What is interesting for us, what is important for us is that you take into consideration, as usual, why we are considering a given solution. Okay? And usually, a given solution is introduced for two reasons. A matter of effectiveness, or namely doing something new in the proper way. What is the novelty here is dealing with dynamic indexing. And the matter of efficiency. Since we say that, look, auxiliary index works but have some problems in terms of efficiency, we can discuss the introduction of logarithmic merging in order to improve some of the performances. Okay? And this principle can be applied to all the documents that we discuss in this class. And let's recap here. What is the problem in terms of effectiveness here? Here, what is the problem in terms of effectiveness? What is the problem we want to solve here? Index does not fit in memory. Good. So we need external solution. What is the problem in terms of efficiency that we want to solve here? Fantastic solution. The fact is that we need to maintain a term ID index, which can be big. Or if we want to use directly terms, the size of intermediate files can be big. So, single pass. Okay? Effectiveness. In this case, the effectiveness is that we have distributed solutions. Why? Because those algorithms work pretty well, allow us to extend the size of the collection that we can handle, but definitely we cannot handle, as an example, the web corpus. So we need the distributed system. And thus we have Mapreduce. What is the effectiveness here? The effectiveness here is that the indexes are changing over time, are dynamic, while up to now we saw static stuff. And so we see auxiliary files, it works pretty well. But unfortunately, in terms of size, we have issues. We can solve it with logarithmic merging. And that is a matter of efficiency, not anymore of effectiveness. Okay? Effectiveness means doing the right things. Efficiency means doing it in the most effective way, in the most efficient way. Okay? Good. Okay. Now, we have seen as an observation that we can actually reduce the size of the index by means of compression techniques. So, the purpose of those slides and this last part of the lecture is to explore compression techniques in order to improve the performance in terms of space occupancy. Okay? Okay, up to now, we know how to do block-based indexing. We know what is single pass indexing and how to explore those techniques. We know the Mapreduce. We know the concept of dynamic indexing in order to deal with the fact that documents in the collection are dynamic, are not static. Now we want to compress the index in order to reduce the size of the whole index. And in particular, what we can do is we can reduce the size considering the two main parts, right? We can reduce the dictionary, namely, we can compress the dictionary component. I remind you that the dictionary component is the component in which we store all the terms that we want to index. Or we can reduce the postings component, namely, the components maintaining a list to all the documents that contain a given term. Okay? In general, in order to understand how to deal with those two goals, we have to get a better understanding, in particular for the first one, to what are the statistics of a term. As you can expect, not all the terms are frequent in the same way, right? I mean, we already saw it. As an example, stop words are extremely frequent terms with very limited size. Okay, so the idea is, can we guess the statistic do we have a model describing the statistic of the terms, and can we exploit this model in order to improve the compression techniques? Okay. Good. Let's take the 10 minutes and then we'll complete the lecture.